Uh, Hi, everyone who's just coming onto the call. We're just going to wait a couple moments to let everyone join. So we'll start in just 30 or so seconds. Okay, I'm just going to get going to a tight schedule today. But just to begin, my name is Zoe Johnson. I'm coming to you from the Rocky Mountains of Canada. And I'm the coordinator for Task Force 3 of the UN International Year for Glaciers Preservation. And it's my pleasure to welcome you today to our event. Just to go over some quick housekeeping rules, this event is going to be an hour long and will end at 6 p.m. Central Time or 10 a.m. Mountain Time. It's being recorded and will be made available later on the official IYGP website, which is going to be linked in the chat. The last 10 minutes or so are going to be used to used to answer audience questions, and that will be after all of our 5 speakers have finished. So I'll ask that you just please use the Q&A function to submit your questions. And then just before we get going, I'd like to just say, in the spirit of respect and reconciliation, we would like to acknowledge that this event is being hosted on the land of Treaty 7 people, which includes the Blackfoot First Nation tribes of Siksika, Kaina, and Piikani, the Stoney Nakoda First Nation tribes of Chiniki, Bearspaw, and Wesley, and the Tsuut'ina First Nation. This area is also homeland to the historic Northwest Métis and to the Métis Nation of Alberta, Canada, Region 3. And I invite those of you who are joining us today from other territories to reflect upon and recognize the land in which you live, work, and play. I'm now going to turn the floor to Dr. James McPhee, who is the lead of Task Force 3 and joining us from down in Chile, to give some opening remarks. So James, please come and join.
Thank you, Zoe. Hello, good morning, good afternoon, good evening, depending on where in the world you're joining us from. I greet you from Santiago de Chile, the Southern Hemisphere, from a very warm summer here. And as Zoe said, I have the task of organizing and coordinating the Task Force 3. For those of you who are not familiar or not completely familiar with this initiative, as you know, the International Year for Glacier Preservation is a global initiative promoted by UNESCO and WMO, and as a global initiative, then it involves a great deal of organization and so on. And so this initiative is organized and subdivided in 4 task forces, which are shown here in this slide. Task Force 1 has to do with a global campaign and raising awareness and everything that has to do with communications and bringing people to know more about our science and our problems and the challenges ahead. Then Task Force 2 has to do with capacity building, organizing workshops, and all sorts of activities to that end. We in Task Force 3 are concerned about research and monitoring initiatives, and Task Force 4 has to do with policy, advocacy, partnerships, and resource mobilization. Of course, all these topics and themes touch each other, and at some point, of course, they should all converge into the global initiative. So this is our side event. Today, we are launching the International Year of Glacier Preservation, and this is our Task Force 3 specific event. As I said before, our main goal is to advance, to accelerate, to galvanize the different monitoring efforts, the different research initiatives that have been occurring over the decades around the world, to come up with better and new initiatives to close those knowledge gaps that have prevented or that are actually increasing the risks to communities and to ecosystems posed by global warming, climate change, and their impact on cryospheric forms around the globe. With that, I invite you to stay tuned and to learn more about what you can do and how you can get engaged in this initiative, and then give the floor to our stellar group of speakers for this afternoon. Thank you very much.
Okay, thank you very much, Dr. McPhee. So our first speaker today is Dr. Corinne Schuster-Wallace. She's the executive director of the Global Institute for Water Security at the University of Saskatchewan and a UNESCO co-chair holder in mountain water sustainability. She's an expert in local water security in rural, remote, and marginalized communities, and she'll be speaking to us today about the human dimensions of snow and ice. Thank you very much for being here, Dr. Schuster-Wallace.
Thank you ever so much for having me. It's a pleasure to be here, and thank you for the land acknowledgement. I'd like to recognize that I'm joining you from Treaty 6 territory and the traditional homeland of the Métis here in Saskatoon in Saskatchewan, Canada. And I've been asked to start this off by reflecting on the human dimensions of snow and ice. And I want to draw your attention to the top two photos, which are actually of the same glacier. It's Peyto Glacier in the Rocky Mountains here in Canada, and it's from the early 1990s in the top, and you can see the second one where we've now got a meltout lake, which is called Lake Monroe, in the early 2020s. And so I know that we've heard from the formal programs so far, but we do know that our cryospheres are changing, and this is why there's such a criticality of research. And many of you will know the stats, but between 10 and 12% of the Earth is permanently covered in ice and snow. 30% is seasonally covered, and that's certainly the case here in Canada, where sort of 60% of our landmass is covered for 6 months of the year. And given that our cryoscapes are changing, we need to understand the feedbacks. We need to better monitor and predict, but we also need to understand the impacts, the opportunities, and how to build resilience to change. And this is for communities and economic sectors, but I've put a photo here of myself. I don't want to date myself. I won't tell you how far back it is, but this is my undergraduate research in Switzerland. And we have to recognize the fundamental value and emotional attachment that we have as researchers of snow and ice and mountains, but also of individuals in terms of a piece of your heart gets left behind on the ice. And as you saw the drastic changes of Peyto, I'm not sure that my grandchildren will actually see where I undertook my PhD studies. And so again, we have these personal connections that we need to think about as well. So I'd just like to share 3 different types of impacts that I would like us to remember as we're hearing from the other panelists here around monitoring and prediction and research. But the health impacts, health being, yes, the presence of or absence of disease, but also WHO talks about the physical, mental, and social well-being. So health being our entire well-being, if you will. And how is it being threatened by our changing cryosphere? Well, outburst floods, avalanches, unpredictability, the extreme events, snow droughts. And so this unpredictability affects our drinking water security, and it also affects our food security. We've often heard of the mountains as the water towers for the areas around them and in the foothills and beyond. And so in our northern communities and where we have remote communities, the changes in ice roads, permafrost integrity, that's disrupting transportation routes, which affects supply chains, but it also affects the personal safety of people traveling in these regions, whether it's by skidoo or by plane or by truck or vehicle. And so we also have to think about the contaminants. And this is something that is becoming more and more a topic of conversation in terms of what's melting out of our glaciers, our ice caps, and our permafrost. And so do we have remobilization of metals and chemical contaminants? What about pathogens, human pathogens, but also pathogens that might affect our crops? From an economic perspective, we've got the changing snow, we've got the timing of melts that's changing in terms of peaking sooner in the spring and then lower flows perhaps in the summer. And so this affects the timing of the water availability, and perhaps it's disconnecting it from the demands, particularly from an agricultural perspective in those plains. And so we also have hydroelectric power generation in many of these mountain regions. And so what does that do for the hydroelectric power generation? Mineral extraction, tourism is a huge issue in terms of the types of economic activities. We have mountain guiding, we have mountaineering, we have heli skiing, we have skiing, we have snowboarding, ice climbing. So all of these things that bring revenue to these mountain regions. And of course, people's livelihoods depend on these economic sectors. And the other thing that I'd note from an economic perspective is that not within nation states, but also between nations, we have varying degrees of infrastructure and access. And so when we're talking about resilience, economic resilience to the changes that we're seeing in the cryosphere, then there are different levels of resilience that are currently available. And so how we develop a more equitable infrastructure and access to some of these solutions becomes really important. And of course, we have cultural impacts, access to spiritual and holy sites. I talked about the different recreation from an economic tourism perspective, but these are iconic of nations, they're iconic of cultures, and they're also activities that we enjoy engaging in. And for some of us who live in these snow and ice and mountainous regions, these are the activities that make it worthwhile. These are part of the choices that we make to live in these places. And we can't forget the people who live off the land as well, hunting, trapping, fishing, and the fact that many of this is cultural icons. And I've just given you a couple of images on this slide in terms of the ice palaces that are around the world, and also some of the other ways that we travel and IYGP, the races that we have. And so we need to think about these impacts, not just from a one dimension, but across multiple dimensions of the ways that we live, work, and play. And so if we're thinking about that and thinking about research and research gaps, I'd just like to share a few that I think are critical that we need to be addressing and that can take on more urgency as part of the year. And that is around knowledge for decision making, because ultimately building resilience, it's about giving people the information and the knowledge to be able to make those decisions. And the first off is that we need better recognition and respect for Indigenous knowledge systems. We need to be able to weave traditional knowledge and traditional ecological knowledge with Western science and modern science for better solutions to the challenges that we're facing in the cryosphere. We need mechanisms for real-time data sharing and early warning systems, and these need to be easy to understand. They need to be accessible to everyone. And part of this is understanding how people make decisions. What information do people need? What formats do they need it in? How do their decisions and actions impact others or impact the cryosphere? And what are some of the information formats that we need and the tools that support these different types of decision-making by different groups? And this then, in turn, has impacts on the ways in which we predict the outputs that we have from our prediction models. And so we really need to think about this across that whole chain of research and information and knowledge synthesis. From an adaptation and resilience, from an action perspective, we need to understand the different pathway options that are available, because there is no one solution that fits all, and we have multiple opportunities, but we need those shared solutions. We need ways in which we can not just share them, but share where they are geographically, culturally, and socially appropriate. We need to share our failures. We're not very good at that. And so what doesn't work and why doesn't it work in certain contexts? And can we adopt and adapt to other local contexts around the world? The policies and programs that support the adaptation and resilience, that support education and awareness, the emphasis, as I said earlier, on the equity piece of it and the leaving no one behind. And I'll come to that in my last slide. But finally, what we need are monitoring and research that's designed to support sustainable ecosystems, communities, societies, and economies. We need to be looking at applied research. We need to be looking at and joining and connecting the research and the researchers with the people and the decision makers that need the information the most and that can use that research. And we need to be using our research to go through to where it can be operated, where it can be actionable, and not just leaving it sort of on the table in a thesis or in a journal article, for example. So finally, I just want to talk about the ways in which we need to embrace equity, diversity, and inclusion. We know the criticality of water, the critical water challenges, and particularly the cryospheric changes that are impacting and adding to these water challenges. So we need to understand barriers to participation in research. We need to be able to learn to work together across disciplines, across sectors. We need to be able to bring sectors and governments into the research. We need to be able to ensure that all voices contribute to innovative water research and these sustainable solutions. And so that requires that we go back to the drawing board a little bit on how we plan and organize research, how we conduct research, and also then in terms of our post-research evaluation, our iterative improvements, and also the ways in which we communicate and share knowledge. And so with that, I'll thank you very much.
Okay, lovely. Thank you so much, Dr. Seuss-Wallace. Our next speaker is Dr. Brian Menounos from the Geological Survey of Canada. He is a full professor at the University of Northern British Columbia and the former Canada Research Chair in Glacier Change. Dr. Menounos is an expert in climate and glaciers, including their past, present, and future, and he'll be giving us a presentation today on how we assess glacier mass change. Thank you, Dr. Menounos.
Thanks, Zoe, and thanks all for joining this morning. So I'd like to give in 8 minutes or so just a very quick summary on how some of the tools we use to assess glacier health, specifically glacier mass change. I'm wearing multiple hats here. I would like to acknowledge all the affiliations that have been quite beneficial for me to do my work. I'm going to give you an example of a large glacier on the Coast Mountains. This is Clean Glacier, taken by me in 2017. It's a vast ice field behind you. It's in the First Nation territory that straddles the Hamatko territory. And what you can see is a very large glacier. What is hard for you to understand, though, is if you came back year by year, you wouldn't see much change on this glacier. However, the surface and the entire glacier itself loses about 1 gigaton of mass per year. So that's about 1 billion cubic meters. So I'll talk a little bit on how the sorts of tools we use to assess that. Thinking about Canada and North America in particular, we have about 36% of the total ice mass on planet Earth. So this excludes the ice sheets, the Greenland and Antarctic ice sheets. And when we sort of think about Canada as a whole, it's about 1/4. Most of it is contained within Arctic Canada, sort of the lower yellow blob. I've rotated the map here. Much of my work is in Western Canada, and Western Canada and the Alaskan glaciers represents a substantial amount as well. So if we were to think about Western Canada and why glaciers might matter, think about a typical stream that's fed by seasonal snow. So this is a hypothesized hydrograph, so just showing the timing of runoff from the particular snowmelt system here. When we talk about glacier runoff, it's really this slice that I've illustrated here as green. So that's the component in late summer when seasonal snow has been depleted. And that's really where the runoff from glacier ice occurs. In a warming climate, in a climate whereby the glaciers are undergoing what we call often glacier wastage, this is where we get a sort of kick. People have referred to this as the glacier runoff dividend. So this is the surplus water that's being fed to these systems when the glaciers are in an unhealthy state. And you can imagine that once those glaciers are gone, you can take away that yellow and green component of the hydrograph. So that's the deficit that we're facing. So it threatens many of these aquatic ecosystems in late summer and times of drought. So some of the approaches that we can use to assess glacier mass change really started at the turn of the last century, whereby glaciologists would visit glaciers, they would observe surface melt, And really, since about 1965 worldwide, and in particular for the government of Canada, there have been a number of so-called benchmark glaciers where glaciologists will go out to the surface, they'll measure the melt in the summertime, and they'll measure the accumulation of snow in the winter, and they'll add those two terms together, and they come up with what's referred to as the net mass balance of a glacier. The advantage is it's a direct measurement. The disadvantage is it's quite spatially limited. So in Canada, we have only a handful of glaciers, unfortunately, that are monitored this way, yet we have over 100,000 that we actually need to understand the mass change for. So that's where we could use geodetic methods. So that's a fancy word for saying looking at the volume change for many of these techniques. So if we were to think about old air photos or to use laser altimetry, known as LiDAR in some cases, we can come up with an elevation surface, and by repeat surveying, we can figure out a volume change. The disadvantage is we can't convert that directly to water without knowing something about the mass or the density of that material. We can also directly measure the mass change using the GRACE satellite, so changes in the gravity anomaly signature. The disadvantage, of course, is that it is a very low resolution technique, also senses seasonal snow and changes in groundwater. So I'll just give you a very quick example of what we're doing in Western Canada. We use an aircraft with a laser altimeter or LiDAR system, and we sort of will cover specific glaciers in the lower map on the right, either twice a year, every year, or perhaps every other year. And this gives us the ability to sort of upscale the point measurements that we might be able to make at a particular glacier. And in this capacity, we can survey several thousand square kilometers of glaciers. So that gives us a better representation on what's going on in our part of the world. So just as an example, 2023 was really a year of exceptional mass loss. The example I gave you for Clean Glacier, I'll go back to that in a second. That particular glacier on average loses about a gigaton. In 2023, it lost something on the order of 4 gigatons. So about a fourfold increase in mass change. It was extremely warm. It was also smoky. So others, including John, have talked a little bit about the surface darkening and how that's an important component here. And what you're seeing on the right here is an example of Peyto and Yoho glaciers and the surface elevation change over the 2022 to 2023 year period. So this is exceptional mass loss that occurred in 2023. Looking at this in terms of Western North America, so most of the glacier in Western Canada, both in terms of observations and informed with a mass balance model from about 1960 to 2020, and then a model which downscales the global climate projections. We see that if we looked at the annual balance, we continue to experience negative mass loss simply because the glaciers are experiencing more energy at the surface, and we're getting more and more negative mass balance. When we convert that to annual mass change, however, we find that really we could be at a point where we're experiencing the most mass loss. And so that glacier dividend excess, we're not going to have that in the bank anymore. So it's a grave concern for many of these headwater streams. And I'm going to, I think I'm going to run out of time, so I'm going to skip that last slide here there. But I was asked also to discuss how our work might benefit the glacier year or vice versa. And I would make the strong argument that much of the work we're doing is observational, informed to some degree, or it informs models. And you really can't improve physically based models without having those direct observations, which we can use to better predict what's going to happen in the future. And I'll leave it there. Thank you very much.
Okay, thank you very much, Dr. Menounos. Up next is Dr. John Pomeroy of the Center for Hydrology with the University of Saskatchewan. He is the co-chair of the advisory board for the UN International Year for Glacier Preservation and is a UNESCO co-chair holder in mountain water sustainability and an expert in hydrology and glaciology. He will be speaking to us today about how observations from instrumented high altitude basins can improve predictions of mountain glacier, and snow hydrology. Thank you, Dr. Pomeroy.
Thank you, Zoe. It's a great pleasure to be here today with this very distinguished panel. And I'll get my slides up, sharing here. Okay, there we are. Hopefully you can see that all right. So I'll be talking about how observations from instrumented basins can improve predictions. So very much following on the theme that Professor Menounos has introduced. And I'll be referring back to Peyto Glacier that Dr. Schuster-Wallace introduced as well, which has been a great outdoor laboratory for myself and many other scientists. So first I'd like to introduce a program of a project of the World Climate Research Program that is really devoted to observations and to developing improved predictions. And that's the International Network for Alpine Research Catchment Hydrology, or INARCH, which is a project of the Global Energy and Water Exchanges Experiment. And it contributes to UNESCO's Intergovernmental Hydrological Program. So it has goals to measure and understand a variety of high mountain processes from natural to human water, to improve their prediction as coupled systems, and to diagnose their sensitivities to climate change, and then propose how we might manage some sustainability in a sustainable manner. So it's a network of over 50 research scientists with 38 experimental basins on 6 continents, and it has strong contributions to the Year of Glacier Preservation and the Decade of Action on Cryospheric Sciences, which is also starting this year. These are where some of the INARCH basins are located around the world, and it's a growing network. So I'm sure we'll be updating this map over time. But some of the countries where that host and operate these instrumented basins, and these are tremendous outdoor laboratories where we not only monitor change but learn about the functioning of these high altitude hydrological cryospheric systems. The one we have in Canada that's operated by the University of Saskatchewan as part of the Global Water Future Observatories is the Canadian Rockies Hydrological Observatory. And this is a network of about 35 stations through the vast area of the Canadian Rockies, covering areas similar to the Alps in Europe. And they are at high elevations, and they focus on forested or alpine or glacier environments, and everything from the snow and ice changes to soil moisture to stream flow to interactions with the vegetation. One thing we do there is a small scale but high resolution version of what Professor Menounos is doing from the plane, and this is flying LiDAR from a drone. And you see it over Peyto Glacier recently, but we also have instrumented sites on the glacier and off the glacier. And these are part of a long legacy of instrumented measurements at Peyto that go back to 1965, which make it just a fantastic outdoor lab. So by combining the spatial data with stream flow measurements and with hydrometeorological data and observations of things such as albedo changes, dust, debris covered ice melt, other things, we can learn and take that learning and improve our models and test our models and refine them. And this is something we've been doing there. What's interesting is when you take a look at the changes that have been occurring in Peyto Glacier, they're dramatic. We've had about 450 meters of glacier toe retreat since 2019 in the last 5 years, and downward melt is also dramatic, as we'll get into. But we're seeing literally the disintegration of Peyto Glacier, a big response to the heat dome in 2021, but also to the exceptional heat and snow drought in 2023. The 5-year vertical ice loss exceeds 50 meters in part of the glacier. This is a decline in the surface. Some of that is due to collapse of an ice cave, but ablation is resulting in about 35 meters of primarily melt over the lower part of the ice. You see lower figures up here simply because the ice disappeared over the 5-year period. So the result is what we're getting, this very truncated glacier that may not last the decade. So we take information such as that to develop models of Peyto Glacier and models that can be used in other parts of the world as well. And one is the Cold Regions Hydrological Model, which has now a sophisticated glacial representation in it. It's been tested and tried in Central Asia, in Nepal, in South America, in Europe, as well as in Canada. So this is giving us a global ability to predict from this. And Caroline Aubrey-Wake, as part of her PhD thesis, took CRIM and looked at a deglaciated future with about 3% glacial coverage left and a warmer, wetter climate at the end of the century. And what we see for streamflow there in red is a much earlier peak, a months earlier peak, flows in late summer less than half of what they are now, but also shifts to much more rainfall, much more evaporation, ice melt declining as the glacier coverage declines, snow melt increasing a bit, and suppression of redistribution of snow by wind and avalanches. So a vastly different hydrological environment due to deglaciation in this case. So this is just a small subset of the sorts of things we can do. I'll wrap up there and simply say that we need to observe, to predict, and to protect. And this leads towards the glacier year and the cryosphere decade. And one set of systems that can be helpful are integrated observation and prediction systems, because they can find the solutions for society that we will need to deal with our deglaciated future. So I'll stop there and thank you very much.
Okay, thank you very much, Dr. Pomeroy. Our next speaker is Dr. Ekaterina Retz, Assistant Professor at the Institute of Geophysics at the Polish Academy of Sciences. Her area of expertise covers the monitoring and modeling of hydrological processes in glaciarized and snow-dominated river basins. She'll be talking to us today about snow and glacier monitoring in the Arctic at the Polish Polar Station, Hornsund. Thank you very much for being here, Dr. Retz.
Thank you, Zoe, for the introduction. It's very nice to be here. Thank you all for this opportunity. Now I will take you to the Arctic areas. And when speaking about glaciers preservation, it's very important to cover Arctic areas as well, because in fact, they give lion's share to global mass loss. And needless to say that observation in Arctic is even more sparse than in general because of difficult accessibility, harsh climate conditions, and sparse population. And among all Arctic areas, Svalbard is characterized by the most intense glacier mass loss among them all. So I will give like an example of this Polish polar station Hornsund as an example of how observations and monitorings are carried out in Arctic. It was founded in 1957 on Spitsbergen, Svalbard, during the International Geophysical Year that was already mentioned previously. And it operates year-round since 1978. And it makes it one of 4 all year-round settlements on the island. Actually, the island is very sparse populated as whole because, in fact, there are more polar bears living there than people. And speaking about accessibility, in order to get here, you need to first arrive by plane to Longyearbyen, and then you have several options, either snow scooter ride from 6 to 8 hours, crossing 2 fjords by sea ice. It's like for experts, of course. During summer, you can reach by boat from Longyearbyen, and it takes from 15 to 20 hours, depending on weather conditions. And the over winter crew and supplies get here by the vessel through from Baltic shore of Poland, and it takes 7 days to reach it. This station can accommodate from 8 to 9 permanent personnel. There are also places for visiting scientists and wet laboratories, on chromatography lab, permanent GPS stations, workshops, storages, boats, snow scooters, all sort of stuff. Actually, it's like a small settlement. There's even a gym, small gym there to stretch muscles after a hard day in fields. Actually, Horston Station is a platform for polar research in general, and there are like very different scientific areas and studies that are carried out based on the station. But we will be focused on glaciology from now on. The main snow and ice monitoring sites are Huntsman Glacier, that is mid-sized tidewater glacier. Tidewater means that it terminates in the sea. You can see like on this photo behind me how it looks. A small mountain air-bearing catchment and unglaciarized Fuglebecken catchment. Huntsman Glacier, though it's mid-size for Svalbard, for me, from my perspective, it's a very huge glacier compared to those mountain glaciers I used to work before. To give you like some example, the distance from the station to the upper stake is 18 kilometers. It can be either reached by snow scooters if the snow-covered stick. Otherwise, it's almost 40 kilometers walk and crampons, so it's hard. Handbrake mass balance has been negative mostly negative during last decades, and during last years, this mass loss accelerates due to increased summer melting and thinning snow cover during winter, and that goes along with trends in air temperatures recorded on the Horston Meteo Station. With Arabin Glacier, we're actually observing how these small mountain glaciers are disappearing in front of our very eyes, and how it affects hydrology and all these characteristics of the environment in this small basin. The Fuglebecken catchment represents sea races and mountainous catchments that become more and more common in Svalbard with disappearance of the small glaciers. And in fact, it's a good example of research catchment. It also is in Arch network that John mentioned previously. There are like all sorts of different multidisciplinary studies here, from snow studies to hydrological monitoring, hydrochemical as a topic, permafrost monitorings, and very nice things like access to electricity, environmental container, remote access sampling, etc. So talking about challenges, they mostly all are consequences of these hard climate conditions in Arctic and like high difficult accessibility. When we talk about development of monitoring system, what comes to mind is more autonomy and going from point measurements to more continuous measurements. Here there are several problems that are not so easily solved. For example, living equipment on the left. In the field on the left picture, you can see the icing of automatic weather station, and on the right one, it's automatic weather station destroyed by a polar bear. Going from point measurements to more continuous measurements, it's also quite a challenge, because here in Svalbard, there's quite a dense cloud cover that prevents us from using most of remote sensing products. Yeah, that's a challenge that is still addressed quite a lot. And the next one, I think it's common not only for Arctic territories, but like for all mountainous and glaciers regions, that from my point of view need to be addressed during such initiatives as global International Year of Glacier Preservation and Decade. It's harmonization of measurements protocols and data reporting standards, and like sharing standards, and like some repositories for all this data that we gather could be easily used in the next steps. I think that's a great thing that needs to be solved. There are lots of initiatives that are going on, but we still have long way to go in that direction. And I want to conclude with some future perspective that we have now Horizon project starting that will focus on impacts of climate change on inland snow cover and permafrost. And it will be partly based on the Horston infrastructure as well. So we're hoping to advance in our understanding further. And I invite you to give any comments and questions after the presentation. Thank you all.
Okay, thank you very much, Dr. Rett. And our last speaker today is Dr. Sophie Violette, representing the International Association of Hydrogeologists. And Dr. Violette is an assistant professor in hydrogeology with the Laboratory of Geology at the École Normale Supérieure de Paris Sciences et Lettres, and Sorbonne University. She will be speaking to us today about groundwater in catchments headed by temperate glaciers. Merci beaucoup for being here with us today, Dr. Violette.
Thank you for the invitation to give this talk as a representative of the International Association of Hydrogeologists. So my talk is about groundwater in catchments headed by temperate glaciers. It is based on a literature review and some pieces of work performed in the frame of the Ice Hike project. It is a partnership with Icelandic and French researchers and local stakeholders. Okay, that's good. Our literature review highlighted that the catchment areas of temperate glaciers are seriously affected by climate change. These catchments are the subject of in-depth studies from the point of view of glaciology and surface hydrology. Groundwater in these same catchments is much less frequently mentioned and even less studied. The few available studies in the scientific literature on groundwater compartment tend to show a particularly high recharge of aquifer by glacial meltwater depends on glacier geometry, mass balance state, and hydrogeological parameters, but varies between 20 up to 50%, according to the literature. A strong connection between surface water and groundwater, and a fairly high hydraulic conductivity in moraine and till aquifer. So these characteristics suggest that groundwater from the catchment area of temperate glaciers in the coastal zone could feed the fresh groundwater reserve offshore. Also, the role of potentially deeper aquifers in fracture rocks remains completely unknown. The following question can resume the main scientific challenges. What are the aquifers' responses to climate change that prevent us from predicting changes in water resources and the associated risks such as landslides, floods, droughts, etc., and economic and human issues? And this question can be declined depending on the targeted area. In the subglacial area, where and when do the water exchanges between the subglacial system and the aquifers occur? At which elevation under the glacier and at which time of the year? This impacts the water pressure under the glacier, hence its basal sliding, and can lead to speed-up events. In the proglacial lake, how much groundwater contributes to and exfiltrates from the lake? It is important to assess their future evolution and prevent lake overflow. In the proglacial area, at which distance from the terminus does the water start to exfiltrate in streams and which proportion is discharged on the surface? This is important for flood risk. The Ice Hike project aims to address some issues with these questions. How much glacial meltwater feeds the subglacial aquifer, here the till aquifer or the basal aquifer in our case? What is the role of aquifer in the spatio-temporal circulation of water through glacial catchment areas? In particular, what is their role in the dynamics of water flow contributing to the surface flow of river and to the flow of the water exported to the ocean? And what impact will the loss of glacier mass due to global warming have on the hydrodynamic regime of aquifers? To this end, an observatory has been set up. The observation will feed the coupled glacial and groundwater flow numerical modeling, and the result will be shared with local stakeholders to provide guidelines and action. The observatory is set up at the southeast of the Vatnajökull in Iceland. The 4 studied glaciers are the fully temperate with proglacial lakes. The geothermal activity is weak in this area, and there are 2 aquifers, the till aquifer and the basalt aquifer, which is partly covered by till. Since summer 2021, we have been recording groundwater levels and temperature in several boreholes that tap either the till or the basalt aquifer. We also record surface flows and water level in several lakes. During the melting season, we perform dye tracing experiments to characterize the subglacial channels, the rate of subglacial water that infiltrates in the aquifers, and the water flow velocities in the subglacial and proglacial area, respectively. As an example of the results, the monitoring of the water level and temperature allow us to identify that the till temperature, shown in red in this graph, follow air temperature trend, shown in yellow, except at some period where the till temperature is constant and the till water level, shown in blue, is low. This means that the flow of warmer water is coming from the warmer basalt aquifer below, as shown in the small picture. In conclusion, we can say that aquifers are a key compartment of the water cycle in catchment ahead by temperate glaciers. Glacial meltwater is a significant contributor to aquifers, and the remainder is surface runoff. Recharge of aquifers by glacier melt is higher in the subglacial zone than in recharge by precipitation in the proglacial zone. Vertical upward leakage from the deep basalt aquifer to the shallow till aquifer may occur from time to time. As a perspective, we can highlight long-time monitoring of the water level and temperature in aquifers is required for a better characterization of their role in the water cycle, and the couple numerical modeling of glacial and groundwater flows will help us to understand and quantify the impact of glacial meltwater on aquifer dynamics. Thank you for your attention.
Okay, thank you so much, Dr. Violet. That was very interesting. We'll now have some opportunity for questions. So if anyone has any questions, feel free to enter them into the Q&A feature. And to begin, we have a question here from Kieran. So given that we have limited resources, would you prefer to start new research projects with intensive localized monitoring or spatially broad but less intensive field measurements? And where would you want to focus your monitoring? And that's open to any of the panelists to answer. Yes, John, Dr. Pomeroy, why don't you go ahead?
I'll start on that. Both intensive localized monitoring and broader scale monitoring have purposes and benefits. And so it really depends upon the objective. For scientific research, in terms of operational processes, and sometimes intensive localized monitoring is very, very useful. But for scientific research that is looking at continental patterns and trends of global changes, then we need the distributed measurements. In both cases, though, there's a dire need for high altitude observations. Weather stations tend to be at low elevations. Streamflow gauges tend to be at low elevations. Snow surveys tend to be at low elevations. And geological, the hands-on glacier mass balance measurements are incredibly sparse around the world. And so we need more of them in both cases, but they serve different purposes.
Did any of the other panelists have comments, or we can move to the next question? Okay, move on to the next question. So here's one. So how can early career researchers get involved in glacier preservation research? Perhaps Dr. McPhee, as the lead of Task Force 3, you could comment on how early career researchers might be able to become involved.
Thank you very much, Zoe. That's a great question, and there's so many different topics. The first thing comes to mind is that the topics that we cover in this initiative are represented globally. We have partners and stakeholders and collaborators in almost every country, every continent. So by reaching out to your maybe your country's universities, or by actually emailing us to the contact emails that have been listed in the UNESCO webpage for the Glacier Initiative, we can definitely help build those connections and those networks to start creating, you know, different new topics and projects for early career researchers.
Mhm.
I guess, Dr. Menounos?
I echo that, and there's nothing that brings excitement to an old guy like me, okay, middle-aged guy like me, than when I see an excited young scientist who wants to get involved. So certainly reach out to all of us. And if we don't have the capacity, I'm sure we in our networks would certainly put you in touch with the person that could find some appealing work for you. So.
There you go. You just need to reach out. And we have another question. I believe this is directed towards Dr. Violette. Are there other tracers that can be useful for monitoring melt and groundwater in the glacial context?
Thank you for the question. As I mentioned, temperature is very simple and quite easy to perform, and it could give good information, but also geochemical or isotopic tracer can be used, and some of them provide some nice information. I think to study the groundwater compartment, the main difficulties is to get access to the groundwater. It's meant to have boreholes. And there are not such many places where in high mountains or where this kind of equipment is available. So, and after, when you have access to the groundwater, and if you can sample the different kind of water that occur in this catchment, that means the ice, the rain, the snow, the surface water, it's possible to check various chemicals component and to check which one is the best for your study.
Okay, thank you. And another question is, what is something that you think is often misunderstood by the public about your areas of research and or expertise? And how would you wish to correct that understanding, or what do you wish were better understood? This is open to everyone. Yes, Dr. Menounos.
I would say one of the components is the timing of flow and the quantity of runoff that is produced from glaciers. Often I see either the public or the media at least stating that glaciers are critical water supplies, and they are in many cases, but it's really about the timing of when that water is released. And I think that's a component that's hard to get across. That's why I spent some time on a little cartoon trying to show that even though it's a small little component of the total hydrograph, it really does matter during times of drought or during the late summer, especially when we get these early season snow off events. It's really that component, and we kind of lose that capacity to buffer those streams, both in terms of water and thermal regulation, when those glaciers are gone.
Yes, you'll go to Dr. Pomeroy and then Dr. Rudd.
Okay, yeah, so following on from Brian's comment, it's crucially important looking at these downstream impacts. So, you know, if you look at the Bow River in Alberta, so fine, maybe on an annual basis, only 1 to 2% of its annual flow is derived from ice wastage or glacier ice melt. But if we look at seasonal flows, it's much higher, and during droughts, much higher. In fact, during the extreme snow drought of 2023, the non-glaciarized headwaters in that area declined, their flows declined about 2/3 to 1/2, pretty well concomitant with the decline in snowpack and precipitation. But the glaciarized catchments, like Peyto Glacier, went up 25% at that same time. And so there's a drought proofing aspect and a flow moderation aspect that is particularly important. Now, does it last downstream? No, I mean, by the time you get to Saskatoon, the ice melt contribution is less than 1%. But if you go into heavily glaciarized catchments like Whitehorse, Yukon, if the glaciers were magically removed from its headwaters, the flows of the Yukon River would decline by over 1/3 immediately, annual flows, with a dramatic drop in summer flows. And that would have tremendous repercussions, very negative ones, on the salmon migration, on the hydroelectric generation and water supply throughout the Yukon Territory.
Thanks, Dr. Pomeroy. Dr. Ritz, did you have a comment to add?
Yeah, I wanted also to follow up that the thing is that importance of glaciers is not only not so well understood by general public, it's still not completely understood by scientists itself, because starting from that there is no one answer for the whole planet Earth. These answers will be different in every local place. From this to the thing that it's so multi-componential and the influence is so diverse from one or different aspect of environment that it still needs to be studied. If in terms of water availability, what already was commented by John Pomeroy before, it's pretty much like relatively understood. There are other aspects like groundwater, for example, that also was mentioned during this talk. For tidewater glaciers, interaction between this glacier matter and environment of sea fjords, like lots of very complicated questions that needs to be addressed, needs to be studied. And there are still not, there are no exact answers for general public for some of these questions. That's also the problem, I think.
Oh, yes, Dr. Schuster-Wallace.
And to take Dr. Ritz's comments one step further, it's that interaction between the glacial retreats and the snow droughts. And for example, while the glacial melt may not be a significant component of the large river flows on the Canadian prairies, the snow is. And so having a snow drought in the mountains combined with glacial recession, combined with a snow drought in the prairies, and that can set up drought conditions and significant challenges for the agricultural producers on the prairies, where we've got 80% of Canadian crops produced. So again, the interactions between the snow, the ice, the surface water, the groundwater, and the timing of the needs of that water, both in the mountains, but also as it flows out down into the plains.
Okay, thank you. Okay, we are almost at the top of the hour, so I'm just going to give one more question. This was asked by Eric, and again, directed towards Dr. Violette. What is a good instrumentation strategy for groundwater monitoring to identify glacier melt and meltwater impact? How far/close to glaciers/rivers?
Okay, thank you. Thank you for the question. I think there are not a unique response to your question. The main way to observe the groundwater compartment is to make direct measurements through boreholes, but you can also use a geophysical method, which are indirect method, which can give you information about the system who are saturated by water, like radar, for example. It's a good tool to observe the water level. Thus, I will recommend maybe first to perform a geophysical survey from the bottom of the glacier towards the proglacial area, and to check at what depth is the water, and maybe if you have the possibility to drill several borehole from the glacier towards the proglacial area. And is the same for the relationship between the river and the aquifer. It's essential that perpendicularly to the river, that there are several borehole to have along the time and according to the season, to have the monitoring of the water flux in between the groundwater and the surface water. So it depends of your system. The distance depends of your system and the properties of your aquifers.
Okay. Oh, yes, Dr. McPhee.
Thank you. So just before we go, because we are running out of time, or we ran out of time, I just wanted to stress one more aspect of that actually process the different talks that we've heard today. And I think it's very important for us to keep in mind as we move on to the year and the decade. And this is that the impacts are highly nonlinear when we go from the climate to the cryosphere to the groundwater, to the river system, and to the communities as well. It's not the same a 5% decrease in flow at some time of the year when you're at certain hydrological conditions or when you're in a drought condition. And the way communities respond to these deficits are very different depending on when they happen, how spread out in time they happen, how suddenly they come, how prepared they are. And the vulnerabilities of the communities can change widely depending on the specific hydrological conditions. So we really have to take all of these things together into account when we design and we move on and get involved in research endeavors in the future. Thank you very much.
Okay, so we are out of time. Thank you very much to everyone in the audience for your time and attention. And thank you very much to all of our speakers for participating today. We look forward to seeing the rest of you into the rest of the Glacier year. And I wish you a wonderful rest of your morning, day, or night, wherever you're joining from. So thank you.
Thank you.
Thank you.
Thank you.